Greetings, AP Chemistry students. I want to go over, in particular, problems 2 and 6 on this worksheet here about the steady state approximation. Just to kind of review things, the first thing I want to point out is that when trying to determine the rate law, you cannot just look at the overall reaction and say, hey, there's one hydrogen and one bromine. So it's first order in hydrogen, first order in bromine. You can only look at coefficients on elementary steps in a reaction. So to find the rate law for this reaction, we need to direct ourselves to the slow step, which is right here. And what we'll find is that what we find first is that there's actually a problem with this mechanism. This should just be a BR, not a BR2, and that should not be part of that step 3. It's not going to affect our rate law, but it is a problem with that mechanism. But anyways, to find the rate law, we need to direct ourselves to the slow step where we can look at the coefficients to get the rate law, which would say that rate equals K times the concentration of Br times the concentration of H2. Now, this cannot be the rate law for the overall reaction because there's no Br, there's the bromine diatomic molecule instead. This reaction has an intermediate of Br. It also has an intermediate of H. We can't have an intermediate in our rate law. So we need to go back to the first step, this fast equilibrium step where the Br came from, and look at it. And for that reaction, the rate of the forward reaction equals the K of the forward reaction times the concentration of Br2. And the rate of the reverse reaction equals the K of the reverse reaction times the concentration of Br squared, because it's got a coefficient of 2 there. So this makes for something interesting, because what we can do is we set these rates equal to each other, and so we get that Kf times the concentration of Br2 equals Kr times the concentration of Br squared. We then want to solve for bromine by itself, so we move the Kr over to the other side. And when we do that, we end up with Kf over Kr, which will just become another constant. And then to get bromine by itself, we need to take the square root of both sides. This is going to say that the concentration of bromine is going to equal the square root of a constant divided by a constant, which is going to be yet another constant. We'll just call that K prime. And then it's also going to give us bromine, the square root of that, or to the 1/2 power. So we'll plug all of that in for Br up here. And so what we get is that our overall rate law is rate equals K times the concentration of bromine to the 1/2 power times the concentration of hydrogen. In other words, it's half order. So if you double the concentration of bromine, the rate increases by the square root of 2. If you quadruple the concentration of bromine, the rate would increase by a factor of 2. If you increase the concentration by a factor of 9, the rate would go up by a factor of 3, and so forth. So this is a really interesting one where we have fractional orders. So if that problem gave you some trouble, you may want to pause this video and try this problem number 6 again, and then come back and watch as I go through the solution on this one. All right, so for this one, we are going to once again direct ourselves to find the order of the reaction to the slow step, where we get that rate equals K times the concentration of A times the concentration of B2. That's a problem because in the reaction we have B2 and then we have A2. So A is an intermediate. So we need to go back to step 1 which is a fast equilibrium step. And so for that, the rate of the forward reaction equals K times the concentration of A2. The rate of the reverse reaction equals K of the reverse reaction times the concentration of A squared. At equilibrium, the rates are equal. So we have Kf times A2 equals Kr times A squared. We move Kr to the other side. So that's going to give us Kf over Kr, which is going to just essentially be a new constant, K prime. And then we take the square root of those. The square root of a constant is yet another constant times A2 to the 1/2 power, and that equals A. So now we will take this and plug it into our rate law for A, which gives us that rate equals, well, a constant times a constant is another constant times A2 to the 1/2 power times B2. All right. So hopefully that helps you out a little bit. Now, for our one new piece of information today, we're going to look at something called the Arrhenius equation. This is an equation that you do not need to know. I mean, it is an equation. It appeared on your kinetics of crystal violet lab sheet, where essentially, if you record K at different temperatures, then if you take the natural log of K and versus 1 over the temperature and you graph them, then the slope of the line equals your negative activation energy over R. Um, but we're not going to actually be doing that. The College Board doesn't expect you to do that. But what they do expect you to be able to notice here is that the temperature dependence of K is related to the activation energy. In other words, if we go back to these graphs right here, right, the rate of a reaction depends on the ability of the molecules to overcome the activation energy barrier in order to uh, have successful collisions and react. And the activation energy barrier depends upon the temperature of the molecules, in other words, how much energy they have, because if you increase the temperature, then you're going to have more molecules that can overcome this activation energy barrier. And so the reaction happens faster. And so if the reaction happens faster, then K in your rate law has to change, because if you consider a standard rate law like rate equals K times the concentration of A for whatever this reaction is, the reaction happens faster when the temperature increases. And the only way that we can account for that is when you change the temperature, the value of K itself also changes. If the temperature goes up, K gets bigger. If the temperature goes down, K gets smaller. And so temperature and the value of K are related mathematically through that Arrhenius equation, but that's because of the fact that as you increase the temperature, more molecules can overcome the activation energy